Hi everyone, so as requested, this is our rotation review. And as I think about it, now I remember that we never had a test about rotation. I think we might have done some quest assignments and things like that. But I understand the difficulty in feeling confident about rotation. So hopefully we can get that taken care of in this week here. So the first thing I did is I just copied these formulas off the formula sheet. So be aware that you have these formulas on you. The formula sheet is your friend, so you can look at these things and make sure you have it to refer to. The second thing is I see in here this formula right here. I'm not sure why that's in the middle of all that, but the fact is that's an oscillator formula that I just don't think it's certainly not part of this, and I don't think you'll need it in general. Okay, so if you look at this, there are a couple different things here. So these two formulas are about the kinematics. In other words, the motion. Okay, we'll kind of talk about each of these topics in a little detail here in a second. Okay, these two are basically the dynamics, Newton's laws, okay, and the torque, which is very important. So that's sort of the dynamics part. And then here we have momentum, angular momentum, of course. And here we are talking about energy. So that's angular or rotational kinetic energy. So if you look at those are important. A couple other relationships to remember is that when we're talking about rolling or things like that, basically the linear velocity is equal to the radius of the object times the angular velocity, and same thing for the linear acceleration is equal to the radius times the angular acceleration. Okay, so I don't want to go over in detail what everything stands for, but I think you'll get that. This top angular velocity equation or angular kinematics equation, low probability of seeing it on the test. Those aren't really useful problems. This idea is pretty big though. But let's go through some different things and just try to get ourselves a little more comfortable with this. Okay, so this graph I actually showed you on the kinematics review, and remember, one of the things that should be comforting is that just about everything in rotation is analogous to the linear. Okay, there are some details that need to be taken care of, but basically everything on this page is the same thing. So if we talk, instead of position written as x, angular position is theta, angular velocity is omega, so we'll change that to theta. We'll change this to omega, and remember we use alpha instead of a. Okay, but everything else on this was the same. So displacement is just basically you measure the change in theta. On a position versus time graph, if you want speed or velocity, what do? You look at the slope. Okay, so the angular velocity is equal to the slope. Okay, the direction, you're going to look at the sine of the slope. The direction usually tends to be not as important in this, but it's still true, sine of the slope. And we know if there's acceleration going on this graph, you're not going to be able to get a value, but you know that the shape will be a curve. Okay, so the slope has to be changing. If we have acceleration, that means velocity is changing, and since velocity is slope, that means slope is changing, so you have to have a curve. Okay, when we look at the angular speed, we look at the graph, obviously. For the direction, we're looking at the sign, positive or negative. For acceleration, remember that is going to be equal to the slope, so we know the angular acceleration is the change in velocity over the change in time, which is equal to the slope. And the displacement, if you remember, is equal to the area, which is still true here. Okay, and then for the angular acceleration graph, again, we don't talk about displacement. We can get the change in speed, change in the angular velocity is equal to the area. And then the acceleration we're going to get from the graph. Okay. And the direction, we're not going to be able to really get the direction the object is moving in, but that's not typically something they ask anyway. Okay. So one of the things you want to do is just keep your head. You may see a graph of angular velocity or something like that. And again, you can interpret it the same way as you do with the linear. Okay. So you know if you have changing angular velocity, you have acceleration going on. And that tells you something about the torque on the object and so on. So remember that that's there. Okay. So for the dynamics part, okay, is that when it comes to the equations, so we need to talk about the torque first. Okay. So torque, remember, is equal to, I think they have on there R F sine theta. Okay. There were several different ways to write it, but I think that's the most common way. Okay. And we also need to deal with, so remember in linear stuff, we have the concept of force. In angular, it's slightly more complicated because it's not just force, it's where it's applied and what direction. So we have torque, and then in the rotational stuff, we also have, instead of mass, we have rotational inertia. So I is equal to rotational inertia, and that just depends on the shape of it. I don't really have a formula for any particular thing. Okay. So torque is more than just force. So when I say that the radius matters, what that means is that R is usually the distance between the pivot point and where the force is applied. So if this is the pivot over here, okay, so it makes a difference if you're applying a force. If that's F1 and that's F2, well, actually, yeah, we'll leave that. Yeah, we can say that the force 1 is equal to force 2, so we'll apply an equal amount of force, but we're not going to get an equal amount of torque. Okay, and the reason why is because the radius is different, that distance between there, so that would be R1, and then all the way over here, that whole distance from the pivot would be R2. I'm having trouble signifying that. Let me do a different color here. So that whole distance there would be R2. So if we look at it, even though the two forces are the same, the one with the greater R is going to generate more torque. So that means that T1 would be less than T2, or tau 2. Torque 1 is less than torque 2. Okay, the angle matters. So if we have if we compare a force here, let me draw it two different situations here. So again, we have our pivot point. So let's say we apply a force F in that direction, and we apply the force F in that direction. Okay, and let's say the two F's are equal again. Okay, so if I want torque 1, if I look at this again, if you look at this thing, basically this means we're looking at the component of F perpendicular to R. So that is R. and that is theta. So this perpendicular component is the only one that is generating torque, and so that would be much less than F1 in the bottom case. F2 is greater. So again, this would be an instance where torque 1 would be less than torque 2. Okay, and it's possible to apply a force that generates a torque of 0. Okay. The other thing is direction. Okay, so forces have direction, torques have direction. And the way we generally specify the torque is that we say that clockwise torque is negative torque, and counterclockwise is positive torque. Okay, so again, if we look at it this way, a clockwise torque would be there, so that would make this pivot clockwise going around this way, and this would be a counterclockwise torque would be something like that. And again, that's our pivot, so that would want to do it this way. So basically, when we're looking at torque, the standard is that positive is in that direction. Okay, don't worry so much, just so you know that opposite directions are opposite signs. But this is the standard if you really want to know. Alright, so rotational inertia is more than just mass. Okay, so distance from the pivot matters. Okay, so one thing I'm pretty sure we did, let's say that we have a, let's say we had like a meter stick with like a movable weight on it. Okay, and so again, we'll have that pivot point over there. So if we compare having that let's say in here compared to right at the end, so remember they have the same mass, but this one was harder to rotate. So if you hold this left end in your hand and you used it to try and rotate, it was harder on this example than with that one. So remember, the farther the mass is, or the farther away the mass is, that means the greater the rotational inertia. So I'm a nerd, so when I go to the grocery store, I notice that when I put the milk all the way at the far end of the cart, it's harder to turn than if I put the milk at the end of the cart that's closest to me. Why is that? That's because there's greater rotational inertia when the milk is all the way at the far end of the cart. Okay? Alright, so let's look at the concept of net torque. Okay? So let's say we have this object here, and I'm going to put the pivot on the right end. Okay? And I just need some values, and I need to make this up. I didn't do this beforehand, so let's say that this is 10 newtons. This one looks a little shorter. Let's say that's 8 newtons. That looks to be about 10 newtons. We'll make this one 10 newtons also. And this one, let's say, is 20 newtons. And then we need some values here. So let's say this is a meter stick. We'll kind of go left to right to left here. So this is going to be 1 meter. So let's say we have 0.5 meters there. Let's say this is 0.3 meters. And this is 0.75 meters. And this would be 1 meter out there. That's a 7.5. Alright, so we want to talk about the net torque. So we look at this, and you're going to need some information here. So let's say that this is 30 degrees right there. Alright, so the net torque is, we're just going to find the torque from each force and add it up. So we're going to think of RF sine theta. So the first one, this 10 Newton force, I picked 30 degrees because the sine of 30 is 0.5. So if I do R, which is 1, times F, so we're going to have 1 times 10 times the sine of 30, which is 0.5. And then you ask yourself, is that positive or negative? Is that producing a clockwise or counterclockwise torque? Okay, so that would make this move down, which would be the counterclockwise. So that means it's positive. Okay. If we look at this 10 Newton force here, that's going to produce clockwise torque, so that's going to be negative. And R is 0.75. Okay, this force is perpendicular to that, so it's just times 10. If you want to think of the sine of 90 degrees, that's fine, you can use that. Okay, this is going to produce a clockwise torque equal to 20 times 0.5. And this is going to produce a counterclockwise torque. Excuse me, this one's going to be a clockwise torque. This one, the 20 Newton force, is counterclockwise. So minus 8 times 0.3. And then this, R is equal to 0. So this force is not going to generate any torque at all. So that's all we have. So now we just do some simple math here. So it looks like we've got 5 minus 7.5 plus 10 minus 2.4. Okay, so I'm going to have 15 minus 9.9. So that'll be equal to 5.1. And that would be in newtons times meters. Okay, so the concept of net torque is analogous to net force, so we have to deal with that. So when we talk about Newton's laws, which are the big part of dynamics, we know we have to know what the net force is. And in Newton's laws, we know that the motion of the object is based on whether the net force is 0 or not. Okay. So Newton's first law says if F net is equal to 0, the object is at rest or constant speed. So torques, same thing. So we know that the net torque is equal to 0, and that means that the object either has to be rest or constant angular speed. Okay. And this is a case where it's pretty rare to have the constant angular speed part. Okay, so I think we did as part of the rotation stations lab before we left, we had this sort of situation. You have a meter stick, you have that little balance point there, and you have these different weights, and you figure that out. So let's say it's a pretty simple thing here. Let's say we've got a let's see. Did some calculations before, make my life a little easier. So let's say we have a 10 Newton force there and a 30 Newton weight over here, and we know that this distance is 0.4 meters, and we want to know what this distance is. Okay. So to balance that out, so if we balance that out, we know that it's going to be at rest. So we know the net torque has to equal 0. Okay, in other words, the clockwise and counterclockwise torques have to balance each other. So we know that 10 times 0.4 has to equal 30 times x. And so that's a pretty simple problem. So we've got 4 divided by 30. And you can do the math if you want to put that into a decimal. Okay, that would be in meters. Okay. The second case is what happens when the torques don't balance out. Okay. And so if you look at that, let's say we have this object that has a pivot point there in the middle and it can rotate. Let me put some numbers on here. So let's say we have a 2 Newton force there, a 3 Newton force here, and a 4 Newton force there. Okay, and this is kind of like this has 2 different diameters, so these are like strings wrapped around there or something like that. And let's say we have 0.1 meter there, and the outer radius is 0.3 meters. Okay, so if we're looking at the net torque, okay, we're just going to look at each force. So if we look at the 2 Newton force here, that's going to produce a clockwise torque, so that's going to be a negative. And the torque is going to be, if you think about the lever arm or the radius of the objects, that's one of the things that makes these cylindrical objects really easy to work with, is that the torque is always just the force times the radius. And so you're going to have minus 2 times 0.3. For the 3 Newton force, that is also going to be a a clockwise torque or a negative torque. So that's going to be minus 3 times 0.1. And the other one's going to be positive because it's going to produce a counterclockwise torque, and that's going to be 4 times 0.1. Okay. And so if you look at that, we've got negative 0.6 minus 0.3 plus oh, I'm sorry, this is not 0.1, that's 0.3 for that lever arm because it's all the way out there, plus 1.2. Okay, so we're going to have 1.2 minus 0.9, which gives us a net torque of positive 0.3 meters. Okay. Now once you have that, you can calculate the angular acceleration, because we know for the second law, we know the net torque equals I times alpha. That's also on your formula sheet. Okay, I believe on the formula sheet they write net torque on the, or excuse me, I write net torque on the formula sheet. I believe they write it as the sum of the torques. That's the same thing as saying the net torque. So calculate the angular acceleration. That's going to be the net torque over I. So we're going to have 0.3 over 2, which would be 0.15, and angular acceleration is just going to be radians per second squared. And then if it starts from rest, what is the angular velocity after 5 seconds? Okay, so we know that we have another formula there. Omega is equal to omega naught plus alpha t. So we've got 0 plus alpha, which was 0.15, times t is 5. So that's 0.75 radians per second. Okay, so those are actually pretty simple problems. Let's see if my page is going to change here yet. It'll do that in a second. Okay, now when we talk about energy, okay, kinetic energy, so let's say that we have something that is rolling, okay, so it is rolling without slipping. So not only is it the velocity of the center of mass, it has translational velocity. Some people call that velocity of the center of mass, but it also has angular velocity as it rolls, omega. Okay, so remember that when it comes to kinetic energy, this actually has two forms. So there's kinetic energy due to translation, which is 1/2 mv squared, but this also has angular kinetic energy. So 1/2, remember, instead of mass, we put in I, that's our measure of inertia, and instead of V, we have omega. So here's a question. So let's say we have this disk traveling to the right at 1.2 meters per second, and it gets to this point and starts rolling up the hill. Okay, it's eventually going to come to a stop there at some height h, and that's what we're trying to figure out. Okay, so the question is, what's h going to be? Okay, and so this is a case when you're doing your problem solving here. In a case like this, hopefully you're thinking energy is going to be the right strategy, especially when you're dealing with an incline. If they don't give you an angle, there's no way to use Newton type stuff or anything like that. So you're going to have to use energy methods for this. But what students will look at and often forget is that they'll go, oh, we have the 1.2 meters per second, but they forget the rotational part as well. So if you're using conservation of energy on the AP test, you should always tell them what you're using. So conservation of energy, and our equation from that would be 1/2 mv squared plus 1/2 I omega squared is equal to at the top here, it's going to have all gravitational potential mgh. Okay, so actually if you write this statement, then they know you're using conservation of energy. That's good enough. But it's nice to see that without any numbers put in there. But some students will forget one or two of these terms, one of these terms. Okay, so now if we just do the math here, I did this pretty quick. So remember that we also have this relationship. They gave us V, so we need to figure out omega. So omega is going to equal V over R. And so omega is going to be 1.2 over 0.2. R is 0.2, and I think I did my math incorrectly. Yeah, I did all that incorrectly. That's not good. So that's going to be equal to 6 radians per second. And then we also need to know I. We can go ahead and figure that out. I for a disk, and on your AP test, if you need to calculate an I, they will always give it to you. Okay, so they'll give you the formula. So that's 1/2 mr squared, or mr squared over 2. And so that is equal to 0.5 times 0.2 squared over 2. And when I did that, I got 0.01. That's going to be kilograms times meters squared. So when you set this up, you're going to have 1/2 times 0.5 times 1.2 squared plus 1/2 times 0.01 times 6 squared. That's going to equal the mass, which is 0.5. I'm going to use 10 to make my life easy for little g, times h. Okay, so now it's just an exercise in algebra. I'll do a step or two more, but I don't have the correct answer on me. So for this first term, let's see. So the first term I got 0.36. You can check my math on that. The second term is the one I messed up. So we're going to have 36 times 0.01, which would be 0.36, and half of that would be 0.18. That's going to equal 5h. So h is going to equal 0.54 over 5. And I'll let you do that. That's going to be in meters if you want a decimal. So that's the energy thing. Okay. Now, I think the last bit is the angular momentum. And so angular momentum, I have to say a lot of the problems or a lot of the questions that I've seen deal more with angular momentum in a qualitative sort of way. Not so much calculation, but the idea of it. Okay, so if you have any rotating object has angular momentum, and again the analog L stands for angular momentum, that's equal to I times omega. Okay, so similar to P equals mv. So capital L is angular momentum. So anything that's rotating has angular momentum, and just like linear momentum, it's not a hard calculation to do. So it's more interesting to look at what changes it. So remember that impulse equals change in momentum. And so that's where they get. So impulse is force times time in the linear sense. So in the angular sense, instead of force, we have torque times the time it's applied for is equal to the change in angular momentum, delta L. Okay, so this, I put this top in here just because it has a string. So if you think about getting that from rest and to get it to spin, if you pull on that string, you're applying a torque for a given time, and so that impulse, or that angular impulse, will change the angular momentum, will equal the change in angular momentum there. Okay, so again, anything we talked about. Okay, so when we talked about on a graph, impulse equaling force times time, on a force equaling the area on a force time graph, if you have a torque versus time graph, then that means the area is going to equal the change in angular momentum. Okay, so again, even though you don't have a lot of experience with this, again, everything corresponds between the linear and the angular. Okay, so when we're dealing again with conservation of angular momentum, very often it is a word problem. Think through this. When this event happens, when something is changed, what's going to happen to the angular momentum of the system? Or this happens to the system, explain why, and you may have to explain that. Okay, so the same thing when it comes to linear momentum problems. You want to think about what is in the system. Okay, so those are the objects. So there's usually more than one. Think about external forces. So any forces that come from outside the system, and if so, are they creating torque? So if there's an external torque, that will change the momentum of a system. An internal torque will not. Okay, so now let's look at this merry-go-round example. So we have these kids on the playground. Okay, we are going to define the system as the boy in blue and the merry-go-round. So this thing going around and this kid are the system. The kid in orange is not the system. Okay, so it's pretty clear he's exerting a force. So is the force from the boy internal or external? Well, since he's not part of the system, that is external. So what is his force going to do? It'll generate torque, and it will change the, let's say it's going to increase. Okay, so the force from the orange boy is going to produce torque and increase the angular momentum of the system. Okay, so yeah, that's what you get your buddy to spin you faster. That's what you do. Okay, if you're really nerdy, you go to the playground and you ask your buddy to apply an external torque to make you spin faster. Okay, so the boy in orange gets it going. Okay, and then he lets go. And now after that, the boy in blue moves toward the center of the merry-go-round. Okay, so as he moves toward the center of the merry-go-round, he is going to have to apply a force to himself, probably a frictional force. If he's thinking safely, he might want to be like sitting on his bum and scooting himself back. Okay, so he might be pushing against the merry-go-round. Okay, that would be an internal force. So what happens to the angular momentum of the system? Okay, that internal force isn't going to change angular momentum, so it's going to remain constant. Okay, but, okay, so we know L is going to be constant, but some change is going to be happening. So it's not that the thing's going to keep spinning at the same rate here. Okay, what happens to the angular velocity? Well, let's think about these two things in relationship to each other. As he moves toward the center, what's happening to I? I is going to be getting lower. Okay, because mass is going toward the center. So as it goes toward the center, the the inertia of the system decreases. And so now when you look at this, if I is decreasing but L is constant, that means omega has to be increasing. So that increases. So again, it's a question we can answer using these big ideas. They don't have to give you a lot of numbers, and so we need to explain our way through these things. Okay. Now the last part of this is the collision scenario, and this one you have to think through. So let's say that we have it pivots around an axis, so my drawings aren't great. So right now this plank is there. Let's say that's the pivot point. This last, I should have had the pivot point up there, but you get the idea. Okay, so when we look at this ball is moving, has velocity v, okay, and then here it collides with it and then sticks to it, and then we have rotation. Okay, so let's say that the system is the ball and the plank. Okay, and then the forces, internal or external. So right now there's a force on the plank by the ball, and there's a force on the ball by the plank. Okay, so now the question is, are those internal or external forces? Well, those are internal. And so after this, we see that we are going to have angular velocity. So we are going to have angular momentum. That's not going to be zero. So angular momentum is equal I times omega, and it's definitely going to be greater than zero. Okay, so now we kind of have to use some reasoning because we're dealing with this in kind of a very big picture kind of way. We said that internal forces cannot change the angular momentum of the system. What that means is that the system, well, angular momentum should be conserved if there are no external torques. Okay, so that means that the system had to have angular momentum before the collision. And you may be asking yourself, and it's a very legitimate question, how can it have angular momentum if nothing's spinning or rotating? And the answer is that this object has angular momentum. Now this is something where I think the AP people, they bring up this scenario on a regular basis, but they don't give you the formula to deal with it. Okay, so let me just say this. I'll give this to you really quick. Okay, so if you have a object moving in a straight line like this, it can have angular momentum. And everything works out if we define the angular momentum here of this ball as saying that's equal to its mass times its velocity times r perpendicular. So the question is, what's r perpendicular? So r perpendicular would be the perpendicular distance between the pivot point and the line that this is traveling on. So that would be r perpendicular. So what we know is that everything works out if we say that something moving in a straight line actually has rotational inertia because it's moving along a line that doesn't go through the pivot point. Okay? So I just want you to think about that. Now in this interaction, this force on the plank by the ball, okay, will generate a torque on this. So that means that on the plank, so that means the plank will gain will gain angular momentum. The ball is going to slow down, so it's actually going to lose angular momentum, but the angular momentum of the system is conserved. Okay? All right, so that's a good place to stop. What I have here on the next few slides are some questions, and I think what I want you to do is go ahead and try those on your own, and then tomorrow or in the near future I will post a video about the answers to these, but I want you to have a chance to think about them after having watched this. Okay, so that concludes this rotation review.